Okay, yeah, hello. So my name is Alex. I am going to share my screen here, and I'm going to talk about why I think profiling is really important, and why we decided this to be our first webinar. So this is really the result of working with you users and researchers. We have something called the consultancy, where we help people run better and faster. And that's the first step that we always go through with profiling, is when people are saying, can you make our code run faster? We take a step back and we say, well, wait a minute, where is your code spending time? And so we think this is a very important step. But there has been a change also in the past few years with the appearance of new tools. And one of the tools that the tool that we're going to present today, MAP, is particularly easy to use. The thing with profiling, it was always something like a cumbersome process, and nobody wanted to learn it. Everybody thought that it was very useful, but perhaps not intuitive or not easy to use. That has changed. So we think that by sharing our knowledge and our experience with that particular tool, which is a commercial tool, then we will get you writing better, faster code. And not only you're going to write better code and faster code, but you're going to learn about your code. You're going to learn about what, there are things that we discovered. In fact, while we were writing that training material, we used the profiling tool itself to actually run the training material faster. So it's something that we have found useful, and we hope that you will find useful as well. So that's it. So I'm going to just exit here and just SSH to my Wika, because I really want to be typing all the commands with you. We're going to check out a code. It's a Python code that contains some C++ in it. And that also points to the fact that profiling, it's the first tool, I think, that we know of, which really allows you to go across the language barrier. A lot of people start in a scripting language like Python, and then they start developing, some parts of it in C++, the parts that actually need to go fast. And it has always been hard to have a profiling tool that was able to cover all that ground. So that's our training material here. I like to go to NeSI, no backup, because I know I have a lot of space there. I don't have to worry about space. And I also have a directory, which is temp in my case. But really, you can check out the code anywhere you want, right? So let me just start from a clear slate here. So we have absolutely nothing here. But the first thing that we're going to do is we're going to load a couple of modules, Boost, Python, and Forge. We're taking just a default version. We're not too worried about the latest Boost, and then we need to do a module load of Python as well. Okay, there we are. So Python, because the example is written in Python. Boost, because it calls the Boost library. If people are familiar with it, that's okay. If not, don't worry about it. And Forge, that's something that we will use for the profiling. We just load it now, so we don't have to load it later. So after that, we just go to the Etherpad, and we just copy that web address, and we do a git clone. So essentially, we're just going to get a repository from GitHub. Takes a little some time, there are some files. This repository contains a lot of code. We're not going to use everything. We're just going to use one little thing from that particular code. And that's the OpenMP part. So we're going to do a cd first scatter OpenMP, and you should see something that looks like that. The next we're going to use a slightly modified version of the code. So we need to check out a branch here. So we're going to fetch all the branches. Git fetch that, I can type that, I think. All right. And this will allow us to check out the solutions branch. So we do git check out solutions. All right, there we are. So that's a slightly different version of the code. So let me just tell you a couple of things about that particular code. So I have here, you know, the solution which I ran previously, and I'm just visualizing that. But it's essentially, imagine that you have an island, an obstacle, something. That's that gray area here in the middle, and then you start to have, you know, you start to throw some waves onto that object, and you can see the waves sort of coming from the left. And what's going to happen is that the waves are going to bounce off that object. But you can see that there's a sort of an area of the object in the shade of the wave, if you want, where there's not much wave. That's not the place where you want to do some surfing. Obviously, you want to do surfing on the left-hand side, you know, where the wave comes. What you can also see is that, you know, the geometry of the object has a little bit of influence on the way the waves are scattered. Now, we don't have to understand a lot about the code, but I just wanted to share with you just basic principles about the fact that the code is computing a wave. The wave is represented as a set of values on a grid. So there's a sort of a grid number of X and Y cells. And on top of that, so for each point of that grid, you know, we're computing a wave value. On top of that, for each node of that particular grid, the wave is going to be the sum of reflected waves on the surface of that object. And so what you can imagine in your mind is that we have three loops, one that goes across the X cells, one that goes across the Y cells, or Y nodes, almost the same thing. And then for each of these points on the grid, we'll have to do a sum of reflected waves. So essentially, we're going to have three nested loops in that particular problem. And that's something that is quite common in scientific computing. Whether you're doing statistics, whether you're doing, you're modeling, simulating some phenomena, it's quite often the case that you're going to have some nested loops. And these loops, as the problem size increases, these loops are going to take more and more time. Okay, so now that we have an idea of what the problem is, so let's build the code. So I'm going back here. We have our directory, and what I'm going to do is I'm going to do Python setup build. Now, if you loaded your environment before correctly, you know, that should just compile as it is. There is a little bit of C code, as I mentioned, so that's why we have to compile. And right now, so we have everything should be compiled. So we have that build directory that contains a shared library. We don't have to worry too much about it. The driver is the scatter.py, right? And if everything worked okay, then you should be able to do Python scatter.py-h because it's a code that actually takes command line arguments, and we can see these options. The most important ones are sort of NX and NY, which give you the resolution in the X and Y grid, as well as NC, but we're not going to change NC, which is the number of contour elements that, you know, the number of things, the little wave elements that we have to add. Okay, the other one that is quite useful is -c checksum, or -c, we can just abbreviate that by -c, and that gives us a number. So if you have to modify the code, you want to run it before, the modification and make sure that things don't change. That's what we're going to do right now. So we're going to run a very interactively, a very small test case, which should run very fast. And we are going to use a checksum. We can also just use -c here. And of course, I forgot to mention scatter.py. So, the checksum is that particular number here. So if you have to modify, you want to improve the code, that's the number that you don't want to change. Keep in mind that, of course, that number is going to change with the resolution. And I just ran a case here, which is very low resolution. So I'm going to stop at this point, and I'm happy to answer any questions, or just give enough time for people to catch up. Let me know. Maybe we should wait 1 or 2 minutes or 3 minutes just for people to catch up, and then we can move over, and I'll then hand over to Mandes, who's going to run the profiler on that particular code.
Oh, yeah, I think having a minute or two to have everyone catch up is a great idea. Anyone have opinions on the pace? Are you guys able to follow along pretty well? You can pop into the chat or Etherpad or speak out loud if you want. Pace is great. All right, nice. Good to know. Thank you.
I would suggest we do the same then at the beginning. So if you could follow up until here, you just add your plus at the next checkpoint after the Python setup build, please.
Sorry, so where should the plus sign go, Mandes?
There where now all the plus signs occur after the Python setup.py build.
Cool. And Chris or Anthony, any questions you want to answer out loud?
So one question was about MAUI. So, the example will work on any computer, but we designed it to the training material to run on MAUI. So the modules names will be different if you run on MAUI. Requires a little bit more work. I recommend that to run on MAUI if possible.
I would suggest, since this is a fairly small scaling code, if you want to run it on MAUI, please use MAUI Ansel node for that. And there we have, for example, the Anaconda for having Python available.
I'll leave it to you, Alex, to decide when we should move on.
Yeah, so I think if people are happy to move on, let's go, and over to you, Mandes.
Thanks. Can you see now my screen? I should just share out my terminal.
I can see it.
Great. So I did the same than Alex did, and for having the profiler, I just want to just briefly introduce that profiler. So there are a couple of profilers out there, and as already mentioned, the ARM map profiler seems to be one of a really user-friendly one. It seems to be easy to use, and that's why we decided to go for it. It is capable to handle quite a variety of different applications, so starting from serial applications up to MPI, multi-threaded application, mixture of these, or even GPU applications. This application could be built with Fortran, C, C++, or Python, so it doesn't matter from which source they they are created. As already mentioned, we also have for that profiler a documentation page. So if you want to go back and recall what we're doing here, just open that page and read there. This application map has kind of two general ways to use. So there's a graphical interface where you can kind of click and select which application you want to use and with which parameter you want to run it. And, so with MPI or OpenMP and so on. We will not go in detail with that. If you want to have a play around with that, just open map and then you will see what to do. We will now concentrate on the command line option to kind of profile your code and then use the graphical interface just for analyzing these data. But first, before we run the profiler, we also want to verify that this application runs well on one of our compute nodes, and therefore we have a submit script, which is called, I just printed on screen here, it's called scatter.sl for Slurm script. It basically defines the resources needed for this application here. At 10 minutes, will not need 10 minutes, but that's the maximum wall time. It's using one thread and eight cores for these, so a multi-threaded code. We also said hint no multi-thread, which means that we do not want to use hyperthreading, so that each OpenMP thread in that case runs on a separate CPU core. Then we also load the modules boost and Python, and we in that script we just rebuild the application from scratch here, which may not be necessary, but we just do for convenience reason. And then we submit the application on one of the compute nodes, but in this time we use a bigger a more detailed grid with 256 elements in each direction. To run that script, we just sbatch this script, so sbatch scatter.sl, and this should be submitted, and then we can check the queue with sq minus, I usually do with sq minus u.user, so for my user, and see it is still pending. When this runs through, it creates an output file. We will have a look in a second. Hopefully, now my job is running. We also can check that there is already the output files created. So now it should be finished. No, it's still running. It's close to finish, I guess. I already have a look in the output file, so I opened the scatter output job id.output, and we see there's again the build output, and then at the end we get the similar output as we had before with a certain checksum. I would also recommend to have a checksum available, or some unique number in your code that you always verify if you make changes in your code, that this still stays with the analytics you want to have. So we will then later on check this number with the profiling just to verify that the profiler don't change the code itself. So now we want to add the profiler, and therefore we change the job script. So we open the scatter.sl and we add, excuse me, before I do that, since we later on want to do something else, so we copy that job script and I will recall that scatter._prof, and then I will modify that one. There I add the module load forge for having the profiler available, and then I add after the S run, since this is a non-MPI application. I added after the S run for an MPI application. You should add the command in front of the S run, and we add map for calling the profiler, and we add the argument profile for telling map that we want to profile the following application. Then we save this and submit this script. So now I would like to ask you to add your plus at the next checkpoint, just to verify that you could keep up to speed for here. If you have any more questions, just keep on asking them.
Hi, Mandes. We've just got a question saying, can you cat scatter_prof.sl while we're waiting?
Sure. Good point. I just added after the S run the map ---- profile. So the profiler itself could add some overhead, or actually it adds some overhead to your application. The amount of overhead usually depends on your application, how granular it is. So I would recommend to not always profile your application, especially not during production, but within your development process, do profiling regularly. So now my profiling is done, and therewith we again got some output files here. I will first inspect them. So I start with the error output file, which is actually not a real error. I mean, there is some general information provided by ARM map, and there are some two kind of warnings. So the first one is about the library, which could not really be fine, and the other one is about the backtrace size, which means that our application calls a library, which calls another library, which calls another library, and so on, and that stack is too deep. But actually, we are just interested in the top layer of the application, so of not the lower level libraries called within there. So we can easily disregard that one. If you are interested in more depth analysis, you can also tweak ARM map and set some specific variable to increase that stack size if you want. Nevertheless, there is now this file created, which is also stated here. It's usually called like the executable name. In our case, it's Python scatterpy, and then how many processes, how many numbers of nodes, how many threads, and then date and time.map. And we will now open that file by just calling map, and then this file name, Python scatterpy, whatever it's called in your case. And when launching that one, we get an additional window, which looks like the following. After the opening, all the the samples will be analyzed, which are collected for in the run, and then we get this nice view. So I will go through that window now. So starting at the top, there's a kind of, they call it main thread activity, which is a timeline showing with different colors what is done within our code. So different color coding means that the dark greenish one is a serial thread application. The light greenish one means that it's OpenMP threaded, so the threads are spawned within that region. And we also have some more overhead in the grayish one, where in our case here, the Python is called, the Python interpreter is called. And we also have some kind of brownish orange one at the beginning. This is initialization phase. So there in the IO is done. So libraries are read in our case. So there's no real file read, but here the libraries are read from the file system. And then we get more information. We get also CPU floating point operation. We can also see how these are going up and down for our calculation. And which could be also very interesting is the memory usage for our application. So we see at the beginning, it ramps up. So arrays are initialized and then it stays almost constant. This is also a nice plot where you can monitor, for example, memory leaks if your application allocates more and more memories that could be suspicious. Then here in the middle, we have a source code view. I just will hide the metrics up here by clicking that button to better see that. So we have a source code view. I will come back to that in a second with some metrics, what is done in there. But I will first point to your attention down here to that table where the most time-consuming routines are listed. So starting with that routine taking up 23% of the whole runtime, and then going to the next one, which takes 17% of the runtime, and so on. And you already see if I click on here, it changes the line in the source code viewer up there, going to that particular line, which causing that computational load down here. You can also go into more detail if you want, for example, with opening that one, and then you can go into that routine and see or inspect in detail in subroutines where the time is spent. So we saw at the beginning here, we have a function called compute scatter wave, which is called in, actually, it's called in our main function in here. So there's no sub-function called in here. So it's the main function of our scatter.py Python script. And this calls then, if we go down here, for example, it calls in the wave CPP, so the C++ source code file. And in here, this line, this line, and then going down, we can go even deeper in opening that one and going into more detail if we are interested in that. But I don't want to go into that detail, but I want to have a closer look what's really taking time in our application. So the most time consuming one is the compute scatter wave, which is what we expect. And then the next two routines, or the next two source code lines taking the most time is first that XC pointer association here. And actually it's also the YC pointer association down here. And the K vector pointer association. Give me a second. So if we now are the developer of this code, we could have a closer look in how we could optimize that one. And actually, for us, while we profiling that example here, we realized, or we wondered, that these 3 lines is taking so much runtime. So it's like 45% of the whole compute time. But actually, these 3 lines are not really necessary. So if we have a closer look, I don't want to go in detail, do too much detail of development here, but if we have a closer look, we see that these loop here, these 2 loops are not really dependent on the XC and YC elements, and even the K vector, which is associated here, is not really used in that loop. So we could move these out of the loop, and actually for XC, the allocation, the association is already done up here, and the other one with the K vector, we could just move up here. So this simple example, we actually want to see the difference in doing that change. So you could now go ahead and change that source code, or just for the sake of time, I would just now change into another Git branch. We already prepared that. So we do a Git checkout solutions 2. And if we have a short look into the scatter py, we will see that the vector association for krec is done here at the top, what I mentioned. And if we go down in the loop here, we will see that these 3 lines are gone. It's not in here anymore. So to see what that changed and also compare the 2 profiles, we just submit the job again with the new with our new source code. And actually, since our job script does not change, so we still call Python with that scatter, which now changed. And actually, don't want to submit that one. I copied that one. So we want to submit this one, where the profiler call is still in here. So I just submit the batch script again. Then wait a few seconds or minutes until this is done. Are there any questions? Could also add another checkpoint just to see if you could follow up.
Or if Chris or Anthony have anything that's coming up that you want to talk through out loud, feel free.
I guess one thing that seems to be coming up with the some problems that people have having is that the X forwarding is not working. So that's a setup. So when you type map, the name of the file, you should have a window coming up. If that's not the case, then very likely I think it's your X that is not set up correctly. Now to fix it, it depends on which application you're using, whether you're using Mobile Xterm, I think Mobile Xterm is probably doing that automatically, but if you're using POTI, then maybe not. If you're using SSH, then it's a good idea to use a dash capital Y when you SSH to Mahuika.
Good point. Thanks, Alex. So actually, I mentioned that one at the beginning, but I want now to check if all my simulations ran through correctly. So I do just do it with -N1. and comparing the checksums. So the original checksum was 19,000, doing the same with the first profiling run, which was this one. No, yeah, this one. So the checksum here stays constant, that's fine. And now doing the same for the last one. Yes, so there are no changes in the algorithms. So now we can open the our profile -1438. And then compare that. Actually, I also still have here our original profile. Then we can compare one by one. And this is the new profile. So in the first place, we already see that the runtime decreased from 10.5 seconds to 3.1 seconds. We also can nicely see that down here. So the actual sampling bars get wider, since we just have 118 samples now, where in the first place we had like 390 samples. But this is related to the runtime. But we can also see that the percentage of light green area, so the OpenMP polarized regions, is much more dominant now. So we really moved a step forward, having more parts of our code now polarized, or maybe the other way around. We got rid of serial tasks of our application. And we also can see now that the profile down here changed drastically. So now we have 67% of our time spent in that computational routine, and then just a few percent in our routines, while beforehand we had significant portions in these 3 lines we got rid of. So I think that the example nicely shows that profiling is really an instrument which helps to understand what is happening within your code. Even if you are a code developer and think you know what's happening within your code, this tool can give you real insight what's done during runtime. And yeah, therewith I would close, and if you have questions to that, feel free to ask.
Thanks, Mandes. And you know, for me as a user of map, I mean, the thing that I really like is just sort of that X-ray machine aspect, where you can see the code inside. Not only you can see the code, but you can actually navigate from the Python to the C++ seamlessly. I think that was a true revelation for me, and that's why I think it's a great tool to be used. Can you say something about MPI code, or how would it work with MPI?
Yeah, I mean, the profiling itself works the same. So there are minor difference, as I already mentioned in the batch script. You have just to add the map profile in front of the srun for the MPI polarized applications. And then the profile itself will also have some more features. So where you have just one process here, you have then your n amount of MPI threads, and you also can go to the threads and see differences in there. But the general overview here will be the same, yes.
So presumably you can also do OpenMP and MPI, is that correct?
Yeah. You can do also hybrids, so OpenMP, MPI. You can also profile GPU applications and monitoring the GPU offload there. Yes, you can do that.
Do you want to mention a little bit the other tools that people could potentially use? If they move beyond RMAP, or do you think RMAP is just the one tool for everything?
No, I mean, we have a couple of tools available. So staying with Profiler, for example, we also have the Cray perf tools, which are another kind of, I mean, it's also profilers, but coming from Cray instead of from ARM. They are working basically the same, so also doing sampling with our applications. To call them, it's slightly different, so you have to load a specific module, the Cray perf tools module, you have to recompile and then just run, and then you can visualize that one. Don't want to go in detail with that, but that could be also interesting if you may, for a certain reason, not trust that profiler here and you want to have a second opinion. We have also other helpful tools for your development processes. For example, debuggers, especially the ARM provides, beside the map, also the DDT, which is a parallel debugger. We also have more debugging tools available beside the usual one like GDB. We will also have Wargrind for HPC and GDB for HPC and so on. So there are a couple of development tools available on our machines, yes.
Would you, I mean, you, because you're a specialist in that, but I was wondering, what's your opinion? What are the shortcomings of map? What are the things that, maybe the other profiling tool might be able to get, and maybe not map, what's your opinion? When you move to PAT report, for instance?
I mean, all the profilers, I mean, there are more than these two profilers out there, but just comparing these two for now. I mean, all the profilers have their speciality and are good in one cases and maybe not so good in other cases. I like ARM map really, since it's really easy to use. You just have to, instrument just change your batch script and just rerun, and you immediately have your results out there without recompiling, without doing anything. It's nicely visualized, I would say. So you have a good overview of your application with the timelines in the top, and then easy to browse through your source code and go to the hotspots of your code. So that's nice. Cray Profiler on the other side has other advantages. They provide maybe more in-depth analysis. You can do beside of what map is doing here, it's called sampling. They can do tracing, which has kind of more details of your applications, and you could also go down and modify it more and exclude certain areas, or just concentrate on specific regions in your code and stuff like that. So yeah, it depends on what you're doing, but I think if you just want to start and just get an overview of your application, map is the easiest way to go. Maybe you want to add something, Alex? I mean, you also used it a couple of times already.
Yeah, I mean, for me, it's really the first entry point is our map, but we do have some material about C profile, but that would only be for Python profiling. And the advantage of cProfile, of course, is that it's open source and you can run it on your laptop or elsewhere. It's completely portable. Whereas here, of course, this is a commercial software. So we have a number of licenses. I think we have hundreds of licenses that we share between RMap and the ARM debugger, which is another tool by the same company. But yes, it's our bread and butter when we do the consultancy. I mean, increasingly we tend to use RMap, but we have used occasionally other software tools as well. They're just a little harder to use, or sometimes they don't give you an insight of the source code in the same way. I think what happened here is we not only did we find the main bottlenecks, but we found the lines, and then we were able to sort of zoom to that particular line and remove it. I think if we had used another tool like cProfile, then maybe we would have found that a certain function was taking a lot of time, but this function could have been called by 3 or 4 different lines, so it would have been difficult to figure out which of the 4 lines was actually consuming most of the time.
Yeah, and I mean, if you are now got interested, I could really just recommend and just play around with that tool. I mean, it has so many other functions we just didn't want to show for now. I mean, just for the sake of time. I mean, you could zoom in here by just selecting an area. You could change the matrices up here, showing kind of beside the default ones also CPU or memory or MPI focused matrices and so on. You could also inspect your output and so on. So there are many things. You can just play around with that windows and just have a few in there. Don't want to overload you with that many details for now. So, but yeah, that's a powerful tool with a lot of functionalities. You should really have a look and just play around.
Well, thanks, Mandes. So I think it looks like we addressed most of the questions, but there's still time for people to ask questions or to clarification about the presentation. Megan, do you want to take over now?
Yep, sure, Alex. I will just ask Chris and Anthony, since they've been hard at work in the question document, if there's anything worth saying out loud, or if someone wants to speak. We have, we're running ahead of schedule, so we have some time to go through some questions if people have something specific they want to cover. So I guess anything from the question document, guys, or not? You've got everything handled there. I
think most of it's been handled as far as I can tell. I mean, unless someone has a specific question they want to ask now.
Cool. Okay, just give a minute, and if anyone has something in mind, you can speak freely. All right. Cool. And I also noticed that there was that third checkpoint that I think Mandes added in the Etherpad. Just curiously, were other people able to get to that point after all, after asking their questions and things? Yeah, so put those plus signs if you were able to get there. Cool. I see a few more popping up now. Nice. That's good to see. Very good. Okay. Well, if there aren't any pressing questions, I'll just move on forward and wrap up our session. There are a few things to bring to your attention, so I will pop my slides back up. Let's see. Share my screen. Okay. So that's our intro slide. So I'll move on to the next one, which is our wrap up. Cool. So we finished the content of the workshop, but before you go, there are just a few things that I'd like to mention. First thing is that we'd love to get some feedback from you on the workshop. This is the first time we're delivering this content, and we want to get better each time it's presented. So if you could go right now to this survey, it doesn't take very long, and I will post the link also in the chat. So let me do that now. Cool. So that link is in the chat. If you could head over there and give us some feedback, what you liked, what you think we could do better, we'd really appreciate that. And also getting support. You probably noticed at the top of the Etherpad that we had these links, but if you didn't, emailing support@nesi.org.nz at any time is the best thing you could do if you have a specific technical issue with your NeSI project. And you can also take a look at NeSI documentation on our map. The link is there, and it's also in the Etherpad. And for full course material is also available for you guys. And that's what was covered today and a whole lot more. So if you want to go over there, feel free. Let's see, and upcoming event. On September 5th and 6th, there's the Science Coding Conference at the University of Canterbury. We'll be doing another version of this training, but it's a bit extended and it's in person. That's going to be a pre-conference workshop for the Science Coding Conference. So if you liked what we covered today and want to go a little bit further, feel free to check out the Science Coding Conference and that workshop. You don't even have to go to the conference to pop into that workshop. They're kind of separate, but the website is just sciencecodingconference.nz. And lastly, we have some webinars coming up. They're just meant to be 30 to 45-minute sessions. Quick things, not quite as hands-on as this workshop, but we'll cover things such as job scaling and running tests, how to share data and set up groups using Globus, and other things. This is our confirmed schedule. If you want to make note of any of these dates, put that in your calendar now. And if you have ideas for future topics for webinars, you can email training@nesi.org.nz. We'd love to get some feedback from you. Any and all feedback is very welcome. And that's pretty much it. I'll share, that's that survey link again. Thank you guys so much for coming along. And yeah, if you had any other questions that have come up in the past 5 minutes, you can share them out loud now. Otherwise, that's it from us. And we really appreciate you coming by. And if you can give us a little bit of feedback by filling out that survey, we would appreciate it. So thanks, guys, and have a great afternoon.